So welcome. My name is Valerie.
And my name is Daniela.
And we're both senior platform engineers at Morgan Stanley working on the Optimus Cirrus platform. So what we're here to do today is show you this platform. We're really excited. It's super cool. We're going to show you how well it works to solve some of the problems that we've had. And we hope you find it interesting. So the Optimus Cirrus platform's been around for about 10 years. We have 1,200 active developers using the platform, mostly for finance-related applications. And it's considered successful. We're growing every day. We're adding new features. So yeah, what you're going to see today is some concepts and some demos. So let's get started.
So let's start by discussing something that we surely have not invented. There is referential transparency. And this is the building block of the Optimus Cirrus platform. Most of you hopefully are already familiar with it, but let's quickly refresh what this means. So imagine I have a function, and if this function is referentially transparent, meaning that all the inputs that of my functions represent all the things that have an effect on my output, then I can do some really cool things with it, right? Because it's guaranteed that given the same inputs, I get the same output, I can do all sorts of optimizations. So for example, what I can do is that instead of calling that function, which might be quite expensive sometimes, I can just cache the result and then reuse it. And this is extremely powerful, but you can imagine that if I was to do that, caching the result and reuse the result rather than calling the function again, if I do that on a function that is not referentially transparent, meaning a function that has some side effects that are not represented in the input of my function, then I'm going to be in trouble, right? Imagine if I have some function that saves some data into a database. If I don't call the function at all, I'm not going to save my data into the database, and that's going to be very, very tricky for my program to recover. But why do we care about referentially transparent functions so much? Turns out that there are a lot of optimization that you can do when you work with referentially transparent functions. We have already seen one of them. This is caching. That is, instead of calling this expensive function, I can just remember the result and then reuse it. I don't need to call the function at all. But there are also other advantages that are really, really cool. Because the only thing that I care about is my input, I can run it whenever I want. I can run in parallel, in background. It doesn't matter. The only things that matters are my inputs. I can also run it wherever I want. It doesn't matter if I'm running on Linux, Windows, Mac, a local machine, a grid of machines. It doesn't matter. The only thing that matters are the inputs. So this allows us to really have optimization on the execution of our program. So let's do a little exercise. We are developers. We try to solve some business problems. And let's imagine that we have a very complex business problem. That is, I have two functions, foo and bar. They produce an integer. They are referentially transparent functions. And then, I have another function called calc that takes an int. I need to call foo and bar, get the results, sum them together. All of these operations are referentially transparent, so we know that we can apply the theory in practice. And let's imagine that foo is doing some crazy calculation. It takes 200 milliseconds, and bar takes 300 milliseconds. This is what I want to do, right? I just want to get the numbers, sum them together. This is not really great. I mean, yes, sure, it works. It solves my business problem. But I'm pretty sure we can do better than 600 milliseconds if we try to approve the theory to the practice. So let's try to do that in vanilla Scala. We can pick several abstractions to do that, but I'm going to pick the one that is more familiar to me. And let's do that with futures. So the first thing that we want to do is that we want to run them in background. And what I'm going to do is just, I'm going to wrap my functions foo and bar into a future, right? Job done, right? Well, not really. Future doesn't really work that way. You need that for comprehension because you need to extract the value once they're ready and sum them together. So let's do that. And of course, you need to change, either you need to wait for the future to complete, or you need to change the return of your function. But the advice that we give people with futures, please don't block them. So we're not going to do that. We're nice people. So we are going to change the return type of our function. And this works, right? Well, no, because then the compiler tells us that it needs an execution context. This is just the information of where what thread pool is going to be used to run our function. So this is great. So now things are running in background, but they're not really running in parallel, right? The way future works is that as soon as I initialize my future, that's when my execution is going to be ready to be executed. So what is happening here is that we are going to wait for foo to complete. Then we are going to schedule bar to run. So they're not running in parallel. So let's do a little bit more change. We are going to save the futures in a file, so they start when they are initialized, and then we extract the futures. So now they are running in parallel and in background. Whew, this is tough. Let's try to do the caching bit. So I know that foo is called all over the place, and I want to somehow remember the results that I've already produced, so I'm going to introduce a new function, which is underscore foo. That is where I'm actually going to put the real implementation of my function. Then I'm going to have a map, which is called foo cache, and I'm going to say, when you call foo, the original function, then look up in the cache, see if I've already computed that value, and if not, produce a value. So hopefully you have realized now how much effort we are putting in execution concerns that have nothing to do with our business logic, right? We just wanted to sum two numbers, right? And we have spent all this effort, and this code is buggy. Get or else, it's clearly wrong. Get or else simply returns a default value. The default value is never going to be added to the foo cache. So this is actually not even working, right? So we now have a lot of code that we need to maintain, and we have a lot of code that requires specific expertise that is associated to the specific abstraction that we picked. In this case, future. And this is fine, right? But it requires some effort from the developers. Now let's see how this would be done in Optimus. And all we have to do is marking our referentially transparent functions with an annotation at node. And then the Optimus Cirrus platform is going to make sure to run them in parallel, cache them, and distribute them if it's something that we want to do. So this is exactly what the Optimus Cirrus is about. So all we ask you is to please write referentially transparent functions. Please mark them as node, and we are going to transform your code with some compiler plugins to have all these good properties that, yes, can be achieved manually, but hey, it's a lot of effort, and I would create a lot of bugs. So when you mark your function with @node, the Optimus Cirrus platform will cache it, run it in parallel and asynchronous, and it will distribute it. So by using the Optimus Cirrus platform, you can finally focus on writing the business logic. And let's be honest, writing the business logic is not usually as simple as summing two numbers, right? That's already a lot of work. Optimus Cirrus will take care of making sure that your code will run as fast as possible.
So you've seen the platform in brief, and as developers, we were building that platform. But platform developers also have complex problems. Surely we can use our own shiny tool to solve our problems. So a lot of our users, as mentioned, are writing finance-related applications, but this model of writing code actually works on any kind of problem. So what we're going to get into next is an example that is hopefully more relatable, and can show you how we've solved our own challenges. So back in 2019, we were in a bit of a difficult situation. Our code base is really large. We had about 5 million lines of code. It is well-structured code. It was well-structured, still is. We have a lot of modules that are hierarchically arranged. And we also had a really high rate of change. So about 100 pull requests a day. That's a lot of changes to keep up with. And this all came together to one really frustrating outcome, an hour of build time. So imagine you're trying to get your work done, and when you need to make changes, it could take an hour. You'd have to go grab your coffee, have a meeting, come back. So this was a very, very bad developer experience. And so we said, what could we do to solve this? Well, we could try writing our own build tool. And if we did that, what would we want in a build tool? So we would want our build tool to be parallel, so that we're making good use of our machines. We want it incremental because, as mentioned, we have all these hierarchical modules. We might as well make use of that. And we want it to be repeatable. So basically referentially transparent, but giving things like, for example, a build should be cross-platform if possible, repeatable on any machine with the same result. So this might look familiar because this is a lot of the same stuff that the Optimus Cirrus platform handles really nicely. And now we're going to give you an example.
So let's imagine that we have our lovely developer, and she's working on an application called app. And she needs to build app. An app depends on data model, and data model depends on utils. And let's see what we want our build tool to do. We are going to call these units of things that we can build scopes. And first version, let's start simple. What do we want our build tool to do? Well, the first thing that we need to do is that we need to build utils. Then once we are done with utils, we can build model and data. And once we are done with both of them, we can start building up. This works, but there is a lot of empty space. We are not parallelizing much. I think we can do a little bit better than this. So let's see what it means to build a scope, what it means to build a unit of work. Well, when I am building something, I need to first download my external libraries. If you are writing a Scala application, there is a good chance that one of your libraries is the Scala language. Then I'm gonna compile my code. That is, I have this lovely text, and then I'm gonna give it to the Scala compiler, and then the compiler is gonna produce some class files, and then I'm gonna package the code. That is, I'm gonna put all of these class files into something that I can run, that being a jar, then being executable. So this is what we have so far. Let's see if we can do a little bit better now that we understand what building means. And we can split things in a little bit better. And now, for example, I know that I can download all the external libraries in parallel. And then if I do that, I can start compiling much sooner. And there you go. My graph is already squeezed a little bit, so I've saved some time, which is great, right? This is a much better build tool. But I bet we can do even better. Let's have a very quick look at what it means to be a compiler. So the Scala compiler is done in phases. And in very high level, what is happening is that we give the compiler some text that for us is code that we know and love. Then the Scala compiler is going to be in phases. It's going to read it. It's going to parse it. It's going to do some magic. It's going to do the type check phase, where it's going to make sure that our code makes sense, is syntactically correct. It's going to do a little bit more magic. And then it's going to produce these class files. And you can see that that's some example code from our scope utils, and that is going to produce class.class. But let's imagine now that I have some code in app that requires some code in utils. And let's start thinking about what is the amount of information I need so that I can start do work in app, and I don't need to wait for utils to be finished. Turns out that all I need in order to compile app is to know that a certain function with a certain signature in utils exists. I don't need to wait for the compiler to compile the entirety of utils. I don't really care what the implementation is about. If utils doesn't compile, sure, I wasted a little bit of my time, but I'm parallelizing more, so I've saved some time. And this is exactly what a special mode of the Scala compiler does. The special mode is called pipelining. And what it does is that we have an extra phase in the compiler that will extract the symbols in my scope so that I can give it to the people that need it, and I can start doing the nesting a little bit earlier. So going back to our definition, our business definition of a build tool, now we know that compile, we can split it in two. And when we say compile, actually we mean two things. We want to extract the signatures, and we want to generate the class files. And back to our graphs, now that we know a little bit better, we can split compile in signature and class. And now we can squeeze a little bit more and do the extraction of the signatures as soon as the signatures of my dependencies are done. So there you go. That was quite a nice squeeze. So we exactly know what we want our build tool to do.
All right, so the next optimization tool we're going to show you is also going to be really helpful in our build tool. So let's make our example a little more complex. I mean, our user probably has multiple apps, and each of these app scopes is going to also depend on data and model. So let's say we're told compile app 1 and app 2. Oh, and to be specific, we're going to focus in on compiling for this section because the libraries and the packaging is not as important for this. So we're going to compile app 1 and app 2. And let's start to build the order of our tasks that we're going to have to run. So for each of these compilation tasks, we're going to need to extract the signatures. We're going to need to compile the upstream scopes. And then we're going to do the rest of our task, process the classes. All right, and now for each of these upstream dependencies, we have to do the same thing. Signatures, upstream dependency classes. And lastly, for utils, we are also it doesn't have anything upstream, so just signatures and classes. And as you can imagine, for data, same thing. And looking at this, you might be noticing that there's a lot of inefficiency. So we're doing this 4 times, and we're doing all of this twice. So what's going to be really critical is that each building block here is a referentially transparent function so that we can use all those nice caching and scheduling utilities that we talked about in the platform. So referentially transparent building blocks, what does that mean? So our outputs, as discussed, class files. We're going to call them artifacts. But what we really need to focus on here is what are the inputs to our function. We need to be able to control and say that anything that could affect the outcome of this compilation task has to be part of my input so that I can ensure the replayability of each function. So what we call that is a fingerprint. And let's begin to think about what needs to be in the fingerprint. In this example, so for our scope, we're going to have a hash of all of the source code. That's pretty useful. Like if the source code changes at all, we're going to have a different hash. We're going to have a mapping for each of the upstreams to their exact versions. We need things like the Scala version, probably the Java version, or library versions. And we're going to need any JVM details or other environmental information that could affect the outcome. So fatal warnings certainly would affect the outcome of your compilation. All right, so with that in mind, we're going to start building our build tool. So what we have here is, I'm going to talk you through the case classes first, the structures. So first thing, scope, simple, it's hierarchical. So we have our strings, and then we have a scope configuration. So this is for each scope, we want each of its upstream dependencies, and we want the hash of the source code within our scope. Next thing that we want is the artifact. So this is a trait. It's just going to have the exact same fingerprint that I just showed you. Sorry, I realize the example is a bit hard to see. It's the same one we looked at. But we need implementations of our artifacts. So we're going to have two kinds. The class file artifact, what's special about this one is that it contains the list of all these paths to the class files that are outputted. And then our signature artifact just contains its unique property is that it has a path to the signature file. Our next piece is this upstream dependencies. So we need to collect all the signatures and the associated fingerprint. So this will be really useful for passing in between our processes to say, like, this is all the stuff you need to have the signature complete. And lastly, we have our build result, which is just a collection of class file artifacts.
Okay, let's see how we can link all of this to the graph that we have seen earlier. So let's focus on our business logic. Let's focus on writing referentially transparent functions, and let's see how everything is going to come up together. And don't worry, we're not actually going to call the Scala compiler. We know that we want two things from the Scala compiler. We want to have the signatures, and we want to have the class files. So we are going to simulate us asking the Scala compiler to do stuff for us with those two functions, extract signatures and do compile. And the first function that we want to implement is build scopes. So I have a list of scopes ID that I want to compile. So what I'm going to do is that for each of them, I'm getting their configuration. Then once I have their configuration, I'm going to compile each of them. That is going to give me some artifacts. And then the artifacts are going to be the result of my compilation. Let's have a look at compile. So what does it mean to compile from a business perspective, right? We are writing referentially transparent function. So when I'm giving a configuration and I want to compile something, what I need to do is that I need to extract the signatures. That gives me the signature artifact. And then I need to get the class file artifacts. And that's it. What does it mean to get the signatures? Well, I need to get some information from my upstream dependencies. So I'm going to represent that with inputs from upstreams. It's essentially going to be, dear dependency, tell me your fingerprint, tell me your signature. Then once I have that, I can give all of that to the Scala compiler. It's going to produce some signatures. And I can put that in my signature artifact together with the fingerprint of my dependencies and my fingerprint, that is my ID and my source version. Let's look at classes, and you are going to see that classes is very, very similar, and that's okay. All I'm caring about is defining my business problem. I'm not trying to optimize anything at this point. So again, I need to get some information from my upstream dependencies. There are their signatures and their fingerprint. Then I need to ask the Scala compiler to do some work for me, and then get the results and put everything together in the class file artifact. And now the interesting bit, inputs from upstream is the information that I need to wait before I can extract the signatures and the classes. Well, I need to see in my configuration which are my dependencies. Then I need to get their configurations. Then I need to get their signatures, right? We already know how to do that, so we're just going to use recursion. And then once I have their information, I can get all their fingerprints and put everything together in my case class. So we know that we have gone through this code very, very quickly, but the point here is that we wanted to show you how we are not worrying about any sort of optimization. This code is really not great. Signatures, we are going to compute signatures over and over again, right? Because if something is a dependency of multiple projects, then we're going to ask signatures over and over again. We know the inputs from upstreams, we are going to ask it twice, right? So this code is not great, but at this point, we don't worry about it. So what we are going to do now that we have made sure that we write referentially transparent functions, and we make sure that all we care about is our business logic, what it means to solve our business problem, Valerie is going to sprinkle a little bit of magic. And that means that she is going to add the at node annotation. And that's it. This is Optimus code. It works. Nothing else that you need to do with it. But of course, don't trust us. So what we are going to do is that we are going to run it now. So we have copied and pasted this code, plus added some log statements, because otherwise it would not be obvious what our program does, and now we are going to run it. And what we are going to see is that we are going to try to compile the same structure that we saw a couple of slides ago, where we have our lovely developer, and she wants to build up 1 and up 2. They both depend on model and data, and model and data both depends on utils. And we are going to see what our program is doing. So the program has started, and we are. We can see that we started by building up 1 and up 2. Sorry. Great, thank you, Valerie. And we have started the compilation. We are doing work, we're extracting signatures. But you can see, look at the timestamps. We are doing a lot of work in parallel. And we're doing work, we are doing utils, model, data, up 1, up 2. We are touching everything, right? This is the first time that we do this. And then at the end of it, we are going to be done with the compilation, and we are going to see that our build result contains 2 class artifacts, one for up 1, one for up 2. And we can see their fingerprint is just the things that they depend on with their source version, plus themselves. Now, let's do a little simulation, right? We want to see the power of Optimus Cirrus, and let's invalidate data. This is the only thing that is changed. And let's compile again, up 1 and up 2. And what we can see is that we are doing some work, right? We are doing work for up 1 and up 2 and data, but model, not doing anything. That has not changed. Why do we have to redo it again? Utils, same. So we are doing exactly the same amount of work. And we can see that in the build results, this is reflected, because now we have 2 class files, one for up 1 and one for up 2. And the only thing that is changed in the fingerprint is that Optimus data now is not version 1, because we have changed something. It's version 2.
All right, so
of course, this was simplification of what we can do with Optimus Cirrus plus the idea of a build tool. This is not the actual build tool. So now Valerie is going to show us the real build tool, the one that we use every day in Morgan Stanley.
All right, so OBT in action. Give me just a moment here. We've got, that's not very visible, is it?
Better? Bit more?
Good? Good. Okay, awesome. So what we have on the top here is the last build that we ran. So we've obscured the names of the modules with the scopes with lorem ipsum. And you can see for each scope, we're going to generate some artifacts. And you can see we have over 1,900 scopes in our project now. So we introduced the problem before, we had 800 scopes. Well, now we've grown. We have nearly 2,000. So, and at the end, we're installing the artifacts. So what I'm going to do, so the lower half is in the same workspace. I'm going to run some stuff. So, well, first, we're going to see where we are. So we're on our main branch. And let's say we just wanted to recompile with no changes, just to see how it goes. And what's happening here is, I should have mentioned, we're now at about 22 million lines of code. So for all those 22 million lines of code, all we've done is hash them, and we've identified that none of our fingerprints have changed. And we did that in less than 4 seconds. So the hashing is super fast, no changes, we're already ready to go, which is really nice, but let's get a little more realistic and see what it's like for a developer who's actually made some changes. So we're gonna check out my feature. And what we've done here is we've modeled a sample feature, kind of realistic. So we're gonna see how many changes there are against main. We've changed 92 files, added a lot of code. And this is something that we have not compiled on here before. And so we're gonna see how it looks if we try to build that. So we've done our cleanup. We're scanning the file system for changes. And we're going to start hashing all of the code and checking the fingerprints again. So for each of these nearly 2,000 scopes, most of them are unchanged. That's why it's going pretty fast. But we did make our changes. So in each case we're hashing, we're going to detect any changes, we're going to extract the signatures of that code, and then generate the classes. And we've gotten right here near the end. For context, the code that we added, it did have, I think, 2 other scopes depending on it, a test scope, I guess 3, a test, another application, and its tests. So we do need to do some actual work here. We have noticed our signature compilation needs to be done. We've noticed the files that were invalidated. This is code about Git things. And we've completed our compilation and generated our artifacts in the 3 scopes that needed recompilation. So build completed in less than a minute. So 2,000 scopes, 22 million lines of code, and we're done in less than a minute. And as you can imagine, this was a really huge deal for our developers. You can actually focus on one task and not have to go get coffee and have a meeting to check if your build is done. Like this right here has totally changed our days and just how we work.
So I have to admit, I've been working on this for a while, but when I see those times, I really get very, very excited. I hope you appreciate how much we have done in less than a minute. 22 million lines of code is a lot.
Yeah. All right, so broadening to some statistics, I'm going to talk you through this one. So we've got two kinds of changes that we measured, and this was in February 2020. I'll get into that in a moment. So our first change we're going to look at here is a really core change. So what the platform developers are doing, changing these really central parts of the code that everything depends on. And then our second change is the more realistic use case for an application developer who doesn't make changes to large parts of the code. They tend to have their application as a leaf on our hierarchy tree. So this was OBT version 1. It's been 3 years, so it's a little better now. But what we have here is, so this is on CI, and in each case, we're going to need to do the same steps. So we're always going to check out the code, we're going to build it, we're going to copy our artifacts to somewhere more stable, and then we're going to clean up. And in this first case, you can see we shortened our build time by more than half. We've also mixed in the copy artifacts in with the build step because it turns out you can do that in parallel as soon as the scope is done. So thinking back to the concepts we looked at, this improvement is primarily from the pipelining that Daniela introduced to you. We're squishing a lot of the timing for things and allowing more parallelization. And our bottom case here, so this is a change without a lot of effect. So this is really where those two concepts come together to make it really powerful. We're going to have the pipelining to squish the things that we actually do compile, but we're also going to benefit from caches for the vast majority of that code that our user has not touched at all. And you can see it's down to about 8 minutes here. We're much improved now in later versions of OBT because we've kept working on it. And also keep in mind, this is for the CI case. So in the local workspace, as you saw, it's a lot lower because you get the in-memory cache. We were using a live build tool that was already started up and had it has caches already for the stuff that you didn't change. So yeah, this was previous state. Now we can't compare, obviously, because we don't have a different build tool to use. And broadening even further, more about...
So we have seen two very core features of OBT that were pipelining and the Optimus Cirrus platform. But of course, you can imagine that a build tool is a little bit more complex than that. So we want to give a big shout out to two open source projects that really helped us make this project successful for us. So the big shout out goes to the BSP maintainers, the build server protocol support. So we have a nice integration with IntelliJ so that our developers can build using OBT, just like they used to do when they're at home with SBT or whatever is the build tool of your choice. And a very big shout out to the Zinc team. This is the incremental Scala compiler. So that allows us to do further optimization when compiling a single scope. So Zinc is going to tell the Scala compiler, hey, only this class is changed, therefore you only need to compile this class plus all the things that depend on it. And as Valerie mentioned, this has been extremely successful for us. We went from 5 million lines of code to 22, 800 scope to almost 2,000. And over time, we have kept working on this. Initially, we were just supporting Scala. Now we also support Java, C++, NPM, Python integration is also coming. So this project that started for us is an experiment of what our platform can do outside the financial world. Well, turns out it's very, very successful and fun to work with. So back to Valerie.
All right, so in summary, we hope we've convinced you of the power of the Optimus Cirrus platform to solve problems when both the execution concerns and the business, like application logic, are both really complex. And we're curious to know what you think. We're excited to share it with you. If you want to know more about how this is implemented, we have some previous talks. You can find them on our GitHub page. We are also open sourcing. Every bit of the demo code you saw today, all the stuff we typed, it's on GitHub. And we're also working on open sourcing the platform itself. The first thing that's coming is the build tool you saw today. We're in the final stretches. There's 12 scopes to go. But you can watch that space if you're curious to see it. And lastly, Daniela and I did not build this alone. There are about 100 developers on our team who are working on various aspects of the platform. And a lot of this is also thanks to them. So now I think we can take questions, if you have any.